We've had an introduction to the Laplace transform. Today we're going to see the benefit of it. We're going to see the main application of it, main use of it, in providing a method to us for solving differential equations, okay, of a certain type. So just a quick zip through what we covered last week and the week before. So we've defined the Laplace transform as this integral transform of a function which is typically written f of t. It's a transform, meaning it's a thing you do to a function that gets you a new function of a new variable. Okay? We integrate from 0 to infinity this exponential e to the minus st times f of t dt. The s is the new variable. Okay? So that integral there that we're looking at in equation 2.4 is a function of the variable s. And it takes account of all values of the function f. Every value of the function f of t from 0 through the whole range of positive reals. Okay? This is written variously. There's lots of different notation and use for the Laplace transform. I mean, the most descriptive kind of notation is this curly L, script L, applied to f of t. That suggests, obviously, the Laplace transform. But sometimes other notation is used, just some kind of notation indicating it's a thing related to f. So f bar suggests a thing related to f, or write the original function in lowercase f, write its Laplace transform with uppercase f. So there are different characters, they refer to different things, but there's a strong link between them. The uppercase f, the Laplace transform, is related to the original function. And the time we've spent so far is looking at this definition, looking at some examples of it, taking the Laplace transforms of some basic functions, but also looking at properties that the transform has. Okay. Here on pages 42 and 43 of your notes, there's an extract from the formula handbook. This shows our table of Laplace transforms. Standard functions down the left, and their transforms down the right column. Okay, so we'll be referring to this lots as we make use of the transform for solving equations, solving differential equations. Also summarized on the second page are some of the important properties of the transform, some of which we have to encounter yet or discuss. So what are these properties of the transform that we need to know about in order to use it to solve our differential equations? There's two main ones for our use, really, that I want to focus your mind on at the moment. The first one is that it is linear. The transform is linear. So when you apply it to a linear combination of functions, so f and g are functions with Laplace transforms, you can form a new function, which is the linear combination of them. When you take that transform, it's equal to the same linear combination using the same coefficients alpha and beta of the individual Laplace transforms. So it's a linear transform. And that's good to know. When things are linear, it means we have a way of dealing with applying them to compound functions manufactured through linear combinations out of simpler functions. Okay? I remember the proof of that was really just a one-line proof, just exploiting the fact that integration is linear. It's a linear operation. When you integrate functions, if the thing you're integrating is a linear combination of simpler functions, the integral of the whole thing is the same linear combination of the individual integrals. Okay? And since the Laplace transform is defined in terms of integration, it inherits the linearity of integration. The second key property was theorem 2.3. Called the transform of a derivative property. If we have a function little x with a certain Laplace transform, this theorem gives us a strict relationship between the Laplace transform of the derivative of x and the Laplace transform of x. Okay. And it tells us that the Laplace transform of the derivative is s times the Laplace transform of x minus this constant, which is the initial value of x. Okay. Now, we proved that last time. It's an exercise in integration by parts using the definition of the transform. But this is the key property that makes it possible to use Laplace transforms for solving differential equations. By iterating the result, applying it repeatedly, you can then generate similar results for the Laplace transform of some higher order derivative of x. Okay, and these always relate the Laplace transform of the nth derivative of x. It's the multiple s to the power n times the Laplace transform of x minus a polynomial in s. And the coefficients of this polynomial in s, the polynomial has degree n minus 1, so smaller degree than the s to the power n term there. And the coefficients, these x subscript i's, these are the various initial values of the function x and its earlier derivatives, earlier than the nth order derivative. Those properties, the ones we most commonly encounter, or the derivatives we most commonly encounter, are summarized here on the second page of the table of Laplace transforms. So you see here the first derivative, second and third derivatives of a function x, and over here are listed the Laplace transforms of them. You see they all depend on this quantity x bar. So x bar here is representing the Laplace transform of the function x, whatever that is. And in each case, it's equal to some multiple of x bar by a polynomial term in s minus some polynomial in s, where the coefficients of the polynomial in s now, the coefficients of it, these x subscripts 0, 1, and 2, are the various initial values of x and its derivatives. So that's a recap of the important properties we encountered last week. So now we're going to show how these all fit together to solve differential equations. So we go to page 48 in our notes. And I'm going to give a short description of the method here and then show you at least a couple of examples. Okay. So this is the whole point of this chapter. It's going to give us the ability to solve differential equations like this. These are ordinary differential equations. The ordinary indicates that the unknown function y is a function of a single variable t. It's not a multi-variable function. So the ordinary means differential equation. So it's an equation featuring the derivatives, fair enough, of y. It's linear, which means that none of these different derivatives of y are multiplied together. You don't see a certain derivative of y multiplied by another derivative of y. Or you don't see any of these derivatives raised to any power. Okay? Each derivative just appears to the power 1. You can have higher various order derivatives, zeroth derivative, meaning the function y itself, first derivative, second derivative, up to nth derivative. They just appear like that. These coefficients, the coefficients ai are constants, so real constants on the left-hand side. But we do allow ourselves, we can have a function, an arbitrary function g of t as the kind of constant term in the equation, so to speak, the term not depending on anything to do with y. That doesn't have to be a numerical constant. That can be a function of the variable t, of the underlying variable t. And we should be able to deal with it as long as this function g is kind of nice and well known. As long as we have the ability to take the Laplace transform of g, we should be able to make progress with solving the equation. Okay, so here's the guideline. It's a 4-step process. I'll just briefly describe it and then go through some examples explaining the various steps as we go. Now, remember the motivation example or the analogy I told you in the very first lecture. We're using the Laplace transform here in a way similar to how early mathematicians, or how we still conceptually would use the logarithm to simplify arithmetic. So if you take the logarithm of a power, it turns into a product. Products are simpler than powers. If you take the logarithm of a product, it turns into a sum. Sums are simpler than products. So here we're going to take the original problem, which is the ODE, which we're trying to solve. We're trying to find the function y that satisfies this. but we're going to transform it. We transform it by taking the Laplace transform of it. So the first step is to find the Laplace transform of the whole equation. Take the Laplace transform of the left-hand side, and you make it equal to the Laplace transform of the right-hand side. Now, in so doing, you see the left-hand side typically of the thing is a linear combination of a bunch of terms. So we're going to have to use the linearity principle. Also, the various terms are various derivatives of y. So we're going to use the transform of derivatives property to relate the left-hand side to make it all in terms of the Laplace transform of y. Now, as part of the specification of the original problem, we may be given certain initial conditions on the solution y. So if we are given those initial conditions on the solution y, they will substitute into the transformed equation. Because remember, when you apply the transform of derivatives property, you get that polynomial in S whose coefficients are the various initial values of x and its derivatives. So if those are supplied to you as part of the problem, we can substitute in those values for those coefficients. We will then have a transformed equation which will have polynomial terms in S in it, and this one unknown quantity, which is y bar. In other words, the Laplace transform of the solution y, which we're trying to find. So we solve the transformed problem to get a solution for y bar. The y bar is a function of S, so we'll get some kind of function of S as the solution for y bar. And then the final step is we take the inverse transform. Once we've identified the function y bar as a function of S, we can take its inverse transform. Now, y bar is representing the transform of y. So when you take the inverse transform, you recover the original function y of t. And assuming you're able to, we take the Laplace transform of the function of S, which we have for y bar, and that will all inverse transform back to a function of t, which will give us our solution y of t to the original problem. Okay? So that's a quick description of the 4 steps. So rather than, just explaining it in more detail, it's best to illustrate it with an example. So there's an example in the notes. I'll write it out again just to emphasize some of the details. I might indicate some extra explanatory steps. And I've got a second example which isn't solved in the notes as well. But I'll emphasize the details of the various steps here. Please do, if you've got any queries about how anything is working, please do stop me and ask questions. So here, the problem is to solve the equation. So this is the second order differential equation. So y is the unknown variable, the unknown function. T is the underlying independent variable. 4y equals 12. Okay. So there's our differential equation. It isn't as complicated as it might have been, because on the right-hand side, we've just got a numerical constant, not a function of t. And we're also given some initial conditions. So subject to the initial conditions, which are that y evaluated at 0 and its first derivative evaluated at 0 are both 0. That's a kind of common setup. I mean, if y was referring to some positional quantity, the position of something at time t, this would kind of indicate that the thing is at rest at time t. It's at some position 0 at t, at time 0, so some reference position, and it's got 0 velocity at time 0, so it's starting from rest. But it's quite common in mathematical modeling and engineering and physics situations that you have a differential equation describing the evolution in time of some property, some quantity y of t, but very often, the initial conditions, the starting conditions of the system would be known to you. Okay, so this is the problem. So the first step is to take the Laplace transform of both sides. Okay, so take the Laplace transform of both sides. And we've got an equation here, so if you do the same thing to both sides, you know, they'll be equal to. So I'll fill in a bit more explanation than is given in the notes, but if I just literally put an L, I mean, you might just choose to put an L on against both sides, but just write it out here just for completeness. Literally, just stick an L around both sides, okay? Taking the Laplace transform on both sides. We then develop that using our known properties of the Laplace transform, okay? Now, first of all, we know the Laplace transform is linear. So what we see here on the left-hand side, we're taking a Laplace transform of a linear combination of these three things, these three derivatives of y, the second derivative, the first derivative, and the zeroth derivative. In other words, the function y itself. Okay? So we can use linearity to say that this is the Laplace transform of the second derivative minus 5 times the Laplace transform of dy dt plus 4 times the Laplace transform of y. And this is equal to, well, okay, here we have the Laplace transform of a constant 12. And we can refer back to our table of transforms. If you look back at your table of transforms, you see that the Laplace transform of the constant 1 is 1 over s. So by linearity, the Laplace transform of the constant 12 will be just 12 times this transform. So the Laplace transform of the constant 12 is 12 over s. Okay, unfortunately there's 5s floating around in here, s's, so you just want to be clear on the distinction between those. So I'll try and make it clear. So that's the coefficient 5 that appears in the problem. That's our new variable s. So what's the justification there? The justification there is using the linearity of L, of the Laplace transform, and the Laplace transform of the constant 1, which is a result from the table. Yeah. But now the things we haven't done anything to yet, these three Laplace transforms, well, there's the Laplace transform of y. Okay, we don't know what y is at the moment. This whole endeavor is to find y, find the solution. So there's nothing we can develop about Laplace transform of y. But there is something we can do about Laplace transform of the first derivative and Laplace transform of the second derivative of y, because we have properties that tell us exactly how these two transforms relate to this transform. Okay. So we're going to employ those. Now, we're going to write, just to say writing L curly brackets all the time, we, what did I do in my solution? I think I used y bar. Yeah, so we're going to write y bar for the Laplace transform of y of t. Just because it's less, it's quicker to write. And now we apply the transform of derivative. Okay. So what's the Laplace transform of the second derivative? Well, if we look at the table of transforms, summarized down here, the Laplace transform of a second derivative is this quantity here on the right. Okay, so we read that off for the function y. So this is going to be s squared times y bar minus s times y of 0 minus the, and I'm going to use the other notation for derivatives here just to get rid of the dy dt notation. So here y prime is dy dt. So that's what the transform of a second derivative looks like. So we leave it there for a moment. Then we've got minus 5 times the transform of the first derivative. First, the transform of a first derivative is also summarized on the table. It comes from the theorem about transforms of derivatives. So it's s times y bar minus y of 0. And then we got 4 times the Laplace transform of y. Well, I'm just writing y bar for the transform of y. And we've still got the 12 over s on the right-hand side. So what we're looking at there is the fully transformed equation. It no longer looks like a differential equation. There's one unknown quantity in it, which is y bar. There's no derivatives of y bar. The nature of the equation has changed. It's changed into a much more algebraic equation. Just this one unknown quantity y bar. It's multiplied by various powers of this new variable s. Okay, but there's no differentiation explicitly going on there. Okay, so that's the culmination of step one. We fully transformed the equation. So step two, it indicated to insert the initial conditions. See, we've got y bar, we've got the new variable s, but we've also got these various constants floating around here, y of 0 and y prime of 0. Now, in this particular equation, we're told that they're 0. So that simplifies the thing a lot. So we will insert initial conditions. And that they're just 0. So the only things that are surviving here the equation simplifies to this one. Okay? The y of 0 and y prime of 0, the first derivative of y evaluated at 0, they are both 0, we're told in the setup to the problem. So the left-hand side just reduces to those three terms there involving y bar. So we're now into step 3, solving this equation for y bar. So y bar is the transform of y. It's some unknown function of s to us at the moment. But you see the left-hand side can be factorized. And then do an algebraic manipulation. And that's kind of the end of step 3. We've solved the transformed equation. We now know what the function y bar is as a function of s. If you want, you can put in the argument s there. It's a function of s. The y bar evaluated at s is this, and that we recognize as a rational function of s, the quotient of polynomials, okay, a constant divided by a cubic polynomial in s. Okay. We're nearly finished. We've solved the transformed problem. Okay. So in principle, there's only one step left now to step 4, which is just find the inverse transform. We can apply the inverse transform to both sides. When you take the inverse transform of the left-hand side, well, the left-hand side is the transform of y. When you take the inverse transform, you just get back to y, the original function yt. And that's going to be equal to the inverse transform of this function of s. Okay. Now what we're going to, the tool we're going to use to help us find that is our table of Laplace transforms. So in principle now we're just going to hit both sides here with the inverse transform. And this will tell us that y of t is the inverse transform of this. Okay, so once we can figure out what this is, and it'll be a function of t, so it's an inverse transform of a function of s, that will be our solution to the original ODE. So our first instinct is to go to the table of transforms and look for this function on the table of transforms. So you're looking down your right-hand column of standard functions and you're looking for that function there. But there's nothing really that looks exact. There's things that look like various bits of this, but nothing that looks like this as a whole. Because this is a constant over a cubic. And try as we might here, we don't really get constants over cubics. Well, we do sometimes up here. If n was 2 here, then this would be a cubic. But then we need to have it fully factorized as a power of a single linear factor s plus a. Other places we've got quadratics or squares of quadratics. Okay, but nothing quite like this exactly. So this isn't to be found yet on the table exactly. So we need to do a bit of work. Okay. So in order to find y bar of s, which is this thing here, on the table, we need to simplify it in an appropriate way. Using its, and what we're going to do is look at its partial fraction expansion. Okay, so this is a common technique in mathematics. Given a rational function of a variable, a quotient of polynomials, we often make use of its partial fraction expansion. Okay? Expressing it as a linear combination of simpler rational functions. Simpler meaning the terms in the denominator are always much simpler. Now this is a cubic, and the first step in finding partial fraction expansion will always be to factorize the denominator as much as you can. It's already got this factor s pulled out. But can we factorize it anymore? Can we factorize that quadratic? Well, in this case we can, because it's -5 is the s coefficient and 4 is the constant coefficient. So that's going to be s minus 4 by s minus 1. S minus 1 by s minus 4. Okay. So these are all s's now on the bottom. So that's quite a nice form set up for finding the partial fraction expansion. You've got 3 linear factors here, s minus 1, and s minus 4. They each appear to power 1. You've just got a constant on top. So the form of the partial fraction expansion we'll need will be some constant alpha over s plus some constant beta over s minus 1 plus some other constant gamma over s minus 4. Okay. Now I think in the solution in the notes, I just produce the partial fraction expansion there. Okay, but I'll remind you of some of the steps of the process we would go through to find the values of those coefficients. So, I mean, the first step will be to put it back immediately over as a single fraction over the same denominator. And the alpha will have to multiply by the product of these two, which is s squared minus 5s plus 4. Beta has to multiply s times s minus 4. And gamma has to multiply s and s minus 1. Okay. So that's putting the sum of those 3 fractions together as a single fraction over the common denominator. And this numerator we're looking at is a big, long polynomial in s. So we'll want to get it into standard form, meaning so we can see clearly what the coefficient of s squared is, what the coefficient of s is, what the constant coefficient is. So let's do that. We have in multiplying s squared, we've got an alpha here. You got beta there, and you got gamma. They're all multiplying s squared. What do we have multiplying s? We've got minus 5 alpha, minus 4 beta, and minus gamma. So multiplying s. And what constant coefficient do we have? Well, the only constant coefficient on the top, constant meaning there's no s in it, is just the 4 times alpha. And that's all over s times s minus 1 times s minus 4. So now we've got our fraction with the numerator expressed in standard form as a polynomial in s. And this has to be equal, you see, back to this original one where you got 12 in the numerator. And the denominators are the same, so the numerators must be the same. These 2 fractions are the same. So this long polynomial in an s must be equal to 12, just the constant 12. So that gives us equating, we compare those polynomials. So equating coefficients of s in the numerators gives us a system of equations for these constants. For alpha, the constant coefficient must be equal to 12. Constant coefficient in the numerator 12 at the top. The S coefficient must be equal to 0. Minus 5 alpha minus 4 beta minus gamma, that must be equal to 0 because that's the coefficient of S in the top, because you can't see an S up there. It means it must have a coefficient of 0. And similarly, the coefficient of gamma squared, alpha plus beta plus gamma, that must be equal to 0 too. So this is what always happens when you set up your partial fraction expansion in the correct way with the unknown constants. You squash it all together again, compare the numerator polynomials, get yourself a system of equations in the unknown constants, what we did in first year with these things, and we then solve this system. In principle, you always have Gaussian elimination algorithm, it's a method for solving these, but since one of them is already really solved, the first one only features alpha, so we can see straight away that alpha is 3. And then that will reduce the other two equations to just being two equations in two unknowns. So it'll tell us that minus 4 beta minus gamma equals 5 alpha on the other side, so 15. And beta plus gamma equals minus alpha on the other side, so minus 3. Okay. So there's no need to go to the full-blown row reduction Gaussian elimination, because just with some simple substitutions we can solve these. See, we can add these two equations together now. So we'll keep the beta plus gamma equals minus 3, but we'll add it to the other equation, and we'll get minus 3 beta, gammas cancel. When you add those two, you get 12. So this is, we've already got alpha equals 3. This third equation is telling us that beta is minus 4. Good. So we should be able to read off the solution for gamma. Beta is minus 4, and gamma, adding gamma takes it to minus 3. Gamma must be 1. Okay. So I'm just doing substitutions here, but in general, and always use your algorithm, the Gaussian elimination, row reduction algorithm for solving the system at this stage. So I've now determined these three unknown constants, so I now know what the function y bar is exactly in this much simpler method. So if I write down the three fractions I had, and I now know the numerators, so alpha is 3, so it's 3 over s plus beta, so minus 4 over s minus 1, plus gamma, so plus 1 over s minus 4. So it's still the same solution y bar of s, but I now have it as in a better form for taking its inverse transform. Okay, I now have its partial fraction expansion as simpler rational functions. So now I can go ahead and take the inverse Laplace transform of both sides. So we're now still in step 4, remember, taking the inverse transform of our solution y bar. The inverse transform is linear, so this is going to be 3 times the inverse transform of 1 over s minus 4 times the inverse transform of 1 over s minus 1 plus the inverse transform of 1 over s minus 4. And now these individual transforms are on the table. Okay? I can look up the table of transforms, consult it. I can read off the inverse transform of each of these. The inverse transform of 1 over s is just the constant 1. So that just gives me the term 3. The inverse transform of s minus 1, some kind of exponential, it's e to the t. The inverse transform of s minus 4 is e to the 4t. And what we're looking at there is the solution, the required solution to the original ODE. That's our solution to the original ODE that we set out at the head of the problem. So that's our first run through. That's our first run through that problem of solving a differential equation using the Laplace transform method. Sorry? A rest. Well, there's only. I was going to take you through another example. The next example is shorter. Aren't it? Yeah, it is short. So I'll show you a second example. Example 2.7. Okay, so you can see it's slightly shorter because it's a lower order ODE. So here we're solving y prime of t plus 2, y of t plus 4, subject to y of 0 is 3. So it's just a second order ODE. I will go through the steps again. I'll be briefer this time. I won't write out the explanation so much because the explanation, the explanation of what's happening is similar to the previous one.
The first one was the first order ODE.
The third order, because it had a third order. Sorry, second order. It said a second order derivative.
This is second order.
No, this is first order because the highest order derivative is the first derivative. So it's called the first order equation. Yeah. Okay, so we take the transform of both sides. We employ linearity, and we use the transform of derivatives property. So it's going to be s times y bar minus y0 plus 2 times y bar equals 4 over s, transforming the constant 4 there as well. So that's transforming by L using linearity of L and the properties about L of a derivative. Okay, those are the same justifications as in the previous example. We then put in the initial conditions. So we have s y bar minus 3. There's only one initial condition there, plus 2y bar, and that's still equal to 4 over s. Now step 2.
Is it linearity of f?
Linearity of L, the transform.
Okay.
The transform process, yeah. And then we're into step 3, solving the transformed equation. Now if you look here, you've got s plus 2 multiplying y bar minus 3 equals 4 over s. So algebraically, we can solve that to get our unknown function y of s. It's going to be 3 over s plus 2 plus 4 over s times s plus 2. Just rearranging the equation, just algebraically solving it. So you got a y bar is a common factor there, factorize it, you got s plus 2, divide both sides by s plus 2, move the 3 over. And step 4, take the inverse transform of both sides. I'm moving quicker here just to fit it in, but the justifications, the explanations of what's going on is tracking the previous example. If you've got queries, do shout out. Okay. So going to step 4, remember these are our 4 numbered steps. Take the inverse transform of both sides. Y of t, the solution we seek is going to be the inverse transform of y bar. So that's going to be 3 times the inverse transform of 1 over s plus 2 plus 4 times the inverse transform of 1 over s times s plus 2. Now, if we look at our table of Laplace transforms, hoping to find both of these here, we can certainly find the first one. 1 over s plus a constant, see that's the 1, 2, 3, the fourth one down, that's an exponential. But 1 over a quadratic, which has no constant term, we don't quite see those anywhere on the table, so we'll need the partial fraction expansion of that again. So just leaving that be for the first part, plus 4 times the inverse Laplace transform. Well, this isn't going to be so difficult to get. We need constant coefficients here to give us back the numerator 1. Well, the only way you get constants is from whatever's here multiplying 2. So in order to get 1, that means there has to be a half there. So that has to be a half. Well, when that half multiplies s plus 2, it's also going to generate a half of s. There are no s's there, so this coefficient here, which multiplies s here, must do the job of getting rid of that half of s. So that coefficient there must be minus a half. So, that's just a quick rip through the whole process of finding partial fraction expansion. But, because the numbers are so nice, you can arrive at it quite quickly. So I first filled in this one because this one has to do the job of generating the constant term when it multiplies s plus 2 and you put it back together. So it has to be a half to give us 1. But it also, at the same time, generates a half s. We have to get rid of that because we don't see an s there. So the second coefficient must be minus a half, multiplies s, give minus a half s, cancels it out. So now we are ready to do a final application of linearity. So the half comes out, you got 2 times the inverse transform of 1 over s, minus 2 times the inverse transform of 1 over s plus 2. Yeah. And now each of those 3 we can find on the table. This is e to the minus 2t. That's the constant 2. And that's minus e to the minus 2t again. Okay, which overall gives us 2 times 2 plus e to the minus 2t. And that's our solution to the original ODE. Okay, but the same 4 steps that we've gone through there. Okay. Same justifications along the way. So here again, we were using the linearity of the inverse transform. And then the justification for the final step at the end was taking inverse transforms from the table. From the table of the plus transform. Any questions about those 4 steps? Okay. We've seen a couple of examples. So if you complete all the ones in question 1, do go on to tackle those in question 2. But we'll go through some examples in the lecture next week as well. Okay, thank you all for your attention, and I'll see you again soon.